Okay, so in class number 22, we are going to be talking about how do you schedule processes for the CPU to work on them. So we'll take a look at several scheduling algorithms and the related circumstances in which you might want to schedule one process over the other. So we are going to be talking about scheduling processes in a computer system here. Okay, so this is going to be the agenda for today. We'll talk about why we need scheduling algorithms, what is the motivation for that, go good CPU scheduler. We'll talk about the various scheduling algorithms. We'll talk about first come first serve. We'll talk about shortest remaining time first or shortest job first. And then we'll also talk about priority and round robin scheduling. And while we are talking about these algorithms, we will also be looking at some examples, some numerical examples. So if you recall the process diagram, so this is sort of the life cycle of a process, right? So even it's new, it's admitted to a reach. A process is essentially waiting for the dispatcher to assign a processor to that particular process so that it can get executed. So the schedule dispatch, whenever it has a CPU ready to assign to the process that is to a processor to it, and that makes the process go from the queue to the. If the process is not be done towards that process, and three things can happen from here. One is it occur and the process may get kicked out from the ready state, meaning it is again waiting for a processor. Or there might be some input request, or there might be some wait for an event to occur. That will put a process into a waiting state. All the time the process waits in the waiting state, that it's essentially increasing its waiting time. And if that particular operation is completed, it goes to the ready queue, and again it is waiting for a processor. The other thing that would happen in running state is that the process may complete and it's up to the minuted state, right? So this is sort of the process state diagram we looked at in the previous class. Focus on the job of this on a particular processor, processes that are waiting in the ready queue. So that's essentially the question that we are answering today. So the decision at each transitions. So as a process goes from one state to the other, and there are 5 of them highlighted over here, the CPU scheduler is essentially making a decision about whether a process gets a processor or whether a process has to be preempted. And if those decisions are good decisions, then we will have some good metrics. Maybe we will increase the throughput, maybe we will reduce the turnaround time, and so on. So we'll take a look at those metrics as well. So some of the definitions: in order to optimize a certain scheduling algorithm, we need to be talking about certain metrics that we are going to consider. The first one is arrival time. Arrival time is essentially the time at which a particular process enters the ready queue, right? So it's the time at which a processor gets admitted into the ready queue. It's in the ready state. That's called the arrival time for that specific process. Next, exit time. So this is the time when the process moves from the running state into the terminated state. So that's the exit time. So job got completed. Process completes its execution and terminates. So you can think of arrival time and exit time as sort of the start and end time for each process. Response time is the time a process spends in the ready queue to get the CPU for the first time. Note here, this is for the first time, because if a process goes from a running state into a waiting state, then it would need the CPU's attention for the second time, but that would not count as the response time. So it's only the time the process spends in the ready queue for the first time it gets the CPU resource. Burst time is the total time taken by a process for its execution on CPU. So this burst time, this is specifically the CPU burst time. So the total time a processor works on a process, that is called the burst time for that process. Now, if it's a very large process, then the CPU burst time may be larger. For a very small process, in terms of its size, the CPU burst time for that may be very small. Next, we'll take a look at turnaround time. Turnaround time is the total amount of time spent by a process from coming into the ready queue, arrival time, for the first time for its completion, exit time. So if you take the end time and subtract it from the start time, that is called the turnaround time. In other words, this is the time a particular process spends either running or it is ready, right? So it is, or it is waiting. So either it is running or it is waiting. Both those times combined is going to be the turnaround time. You can also calculate it as simply exit minus arrival, end minus start, or stop minus start. That's turnaround. Waiting time is the total time that is spent by a process in the ready state, waiting for the CPU. Now, this might happen once or it might happen many times, where a process needs to wait in the waiting state. So altogether, the total time spent by a process in waiting state is your CPU time, waiting time. And again, you can calculate this using the turnaround time here, which is turnaround time minus the burst time. So burst time is how much time did you spend on a CPU, right? So how much time did the CPU spend on working for that process? That's burst time. Turnaround time is stop minus start. The remaining, if you subtract those two, that is going to be how much time a process had to wait in the waiting state. So that's how you calculate the waiting time. Quantum time, which is a parameter of interest for specific scheduling algorithms, is essentially a constant, a fixed time slice or a time share that you can allocate for each process. And we do that for fairness in terms of processes. We'll talk about time quantum and time slice when we look at round robin scheduling. The next one is throughput. Throughput is a metric that we want to optimize, right? We want to have a lot of processes complete in a given amount of time. So the number of processes that get executed by the CPU in a given amount of time is the throughput. And we want the throughput to be as high as possible. We want our turnaround time to be as low as possible. We want our waiting time to be low as possible. But we cannot say anything about the time quantum just yet. There are some trade-offs that are associated by when we choose a fixed time quantum that is large or small, and we'll talk about that. But if you look at the first two, turnaround time and waiting time, we want these to be very, very small, and we want our throughput to be as high as possible. Now, what are the goals for a CPU scheduler? Well, at each transition, you would want the CPU scheduler to make good choices. And those choices might lead to optimizing a certain parameter. So for example, we may want to maximize the CPU utilization, which essentially means I want my CPU to not sit idle. I want it to be executing a certain process, or work on process 1 or work on process 2. I want that CPU to be working. I don't want it to be idle. So that's maximizing CPU utilization. Or you might want to maximize the number of processes that are completing per second. In other words, I want to increase throughput. Or you may want to minimize average turnaround time. Or you may want to minimize the time that the process or a set of processes on average spend in the waiting state. Or you may want to minimize variations in response times. So for example, if there are big variations in terms of burst times for a particular hold on 1 second, what is going on? Encoding give me 1 second, you guys. I think the recording is going haywire. Are you guys able to hear me clearly? I'm having a little bit of a difficulty in recording. I see. Okay. Okay, so the recording might be messy today. Anyway, let's come back to this. So the point is that we have several parameters of interest that we might want to optimize. The problem is that optimizing for different metrics could be conflicting to each other, right? Which essentially means that we could have a situation where we have to compromise or have certain trade-offs. So for example, if you want to maximize CPU utilization, we may not want to carry out too many context switches. Context switch essentially means the change of whatever process the CPU is working on, right? So if a CPU is working on process 1 and if it switches over to process 2, that is a context switch. So if the CPU is spending time doing context switches, then our throughput is going to get affected. Even our CPU utilization is going to get affected because you're spending time doing that context switch as opposed to actually working on a process. But that actually conflicts with CPU utilization because we want to have the CPU work on a process, one process or the other, make progress. So if you want to do, if you want to make progress, what do? Well, if you want to increase CPU utilization, we saw earlier that you increase the degree of multi-programming. You initiate more processes so that even if one becomes slow because of maybe some IO activity, it is waiting for certain event to happen or some IO operation to complete, the CPU has certain other options to work on, right? So as you're increasing that degree of multi-programming, you are increasing CPU utilization. However, this might lead to you spending more time doing context switching, which is again going to decrease CPU utilization. So these sort of metrics are going to be conflicting, right? So it's not that you can just go on for optimizing one. You have to sort of think about a balance between these metrics. Next. Now, what is the basis for scheduling? Well, a process execution alternates between bursts. Bursts are essentially the times at which the processor or process is either going through its execution phase or it is waiting for certain slow input output activity to happen. So the bursts are essentially classified as CPU burst, where a CPU is actually working on a particular process, or IO burst. IO burst is CPU is not working on the process, but the process is sort of waiting for this slow input output operation to complete. CPU burst durations have been extensively been measured and they have been reported. What people have found is that they vary greatly among processes and computers. They invariably tend to have a pattern, and we'll talk about what that pattern is and how does the distribution of CPU bursts look like on the next slide. The relative frequency of each burst duration is what we are going to monitor. It actually tends to have a exponential or a hyper exponential distribution. So let's get to the next slide and take a look at the distribution of CPU bursts. So here you have a distribution of the CPU bursts, and on the x-axis distribution in milliseconds that have that particular distribution. And as you can see from this, that is sort of the result of experiments over many computers that have been extensively been measured. There is a high number of processes for which the burst is pretty small, and something seconds. So lots of processes for which the burst duration is about 3 milliseconds. But as you increase that burst duration, you have a number of burst duration. So the process is essentially sort of alternating between a CPU burst and a IO burst. Now the duration of the CPU burst, as I said, that's what we are sketching over here, right? So let's take a look at what that signifies. As I said, that is centered at 3 milliseconds. That is essentially identifying all the processes that are IO bound, which essentially means that they are CPU. Those are processes that are getting the CPU's attention, and they may need to do some IO activity. So they are bound to do that IO operation. So many short bursts, a big frequency number, burst duration of about 3 milliseconds, processes that are getting the CPU's attention, but IO, so they're also called IO bound programs. On the other hand, there are fewer long bursts, but these are CPU bound programs. So these are maybe going through some slow input output activity, and after that input output activity gets completed, they will be getting the CPU's attention. Hence that's why they are called CPU bound programs. So they are fewer in number, but they have a long burst duration. Now we can see that a good scheduling algorithm takes care of this big discrepancy between short bursts and long bursts. So it would be ideal if our scheduler was allocating maybe 3 milliseconds or maybe 4 milliseconds to each process, so that that CPU attention. That's the burst rate for the number of processes. So that's what a good scheduler is trying to do. From this pattern, a peak at 3 milliseconds, they would adjust maybe their time slice or time quantum, or maybe their whatever algorithm they are following, they make sure that they spend milliseconds for each process. So the CPU scheduling algorithms we will look at today are first come first serve, very simple, but it doesn't suit time sharing systems. We will take a look at shortest job first. We will also take a look at shortest remaining time first. The first come first serve is simple, right? So if you come into the ready queue first, you will get the CPU's attention first. The scheduler dispatcher will assign the CPU to the process that is newer. So first come, you get served first. So it sounds very simple, but it has a lot of problems. And it's especially not suitable for time sharing systems. What are time sharing systems? These are systems, essentially operating systems, in which there's one processor, but there are multiple processes that are doing a time sharing for that particular processor, right? So process 1 uses the CPU resource for time 1 to time 2. Then process 2 uses it from time 2 to time 3 and so on. So that would be a time sharing operating system. So that's what a first come first serve is. It's not suitable for time sharing, but it is very simple. And it has other problems. We'll take a look at those examples when we take a look at a numerical example here. The next one is shortest job first. This one performs really well, but it is purely theoretical, because for you to do this, you need to know what is the shortest job, and it is impossible for an operating system to know which job is shortest at the start of the execution. So we can sort of approximate a shortest job first with a prediction for burst time. So we'll take a look at some prediction that we can do for the burst time. So we can sort of approximate a shortest job first. The last one is a practical approximation to shortest job first, called as the shortest remaining time first. So we'll take a look at these three in detail. First, let's start with the first come first serve scheduling. So how does this work? Well, it is simple, the simplest actually CPU scheduling algorithm. All the CPU does is the requests that are coming in first will get the CPU first. It is good for for a specific order of processes coming in, but it can be very bad if that order of processes coming in changes. That's a problem. Implementation is managed by a first in first out queue, as shown over here. There's a tail of the queue all the way over here, there's a head of the queue all the way at the front. So when a process enters into the ready queue, the process control block for each process, there's a process control block. That PCB is linked to the tail of the queue. So you come in to the ready queue, your PCB will get linked to the tail of the queue so as to enter the FIFO. Then when there is a free CPU, the CPU is allocated to the process at the head of the queue. So first in, you came in first and you move to the right and you get out first. So that's your first in first out queue. Also a part of the first come first serve scheduling. So even though it might seem sort of pretty straightforward, we're going to see that this can lead to some serious issues. And we'll look at those issues by going through this particular example. So suppose there are three processes and calling the three, they're all, for example, say in the so they have all arrived. Maybe they have arrived at the same time. Are ordered, right? So Q comes first, B comes in, and P comes in. It's not particularly to note their arrival time. I'm just assuming at this point that they are a bit staggered at the same time, but they are coming in that order: P1 first, P2, P3 next. The burst time, or CPU burst time for each to us. We have 4 milliseconds for P1, we have 3 milliseconds for P2, we have 3 milliseconds for P3. Now, actually P4 is 28 times than P2 and P3. So first serve scheduling, first, then P2, and the last that gets executed execution is P3. And first come first serve is actually not even preemptive, right? So if you're working on P1, you have to complete it in order to move to P2. It's not preemptive. You're not kicking P1 out because it's too long. Which essentially means that theoretically, like just for the sake of discussion, if P1 was 50 milliseconds, extremely long, then and even though they are very short duration, short bursts, they require only short bursts, they are waiting for a very, very long time, right? So one process could simply hog up all the CPU resources and not let any progress be made by the other remaining processes. So that's one problem, one of the problems in first come first serve. So let's talk about an average waiting time metric that we will try to calculate here. So process 1 comes in first, for example, and right away, because it is the first come, we serve it first. So the CPU, the scheduler dispatcher, assigns a CPU to process 1, and the process 1 goes from the ready queue to the running state. It did not have to wait for the process, which means that its waiting time is 0. It didn't have to wait. But even though it might come at maybe 1 millisecond or 2 millisecond, it doesn't matter. It came, soon after P1. There was no progress made on P2 until 24 milliseconds because we were working on P1 and we did not kick it out. Non-preemptive. P2 had to wait for 24 milliseconds because of that. But after about 27 milliseconds, P1 was complete, P2 was complete, and then P3 came in to the running state, but it had to wait for 27 milliseconds before it made any progress. So if you look at the waiting time for P1, P2, P3, P1 didn't have to wait for a processor, P2 waited for 24 milliseconds for it to be running, P3 had to wait for 24 milliseconds for it to be running. So to calculate average waiting time, if you take the average of all these three numbers, you get 17 milliseconds. So on average, the waiting time for these three processes was 17 milliseconds. That is the average time to begin executing any of the process. So milliseconds, well, it is high. A bigger problem is that it totally depends on the order. Now imagine a situation if P2 comes in first, P3 second, P1 comes in last. If P1 comes last, the first come first serve scheduling algorithm, the numbers seem very, very good. So we are totally, if P2, if the processes can be, then our time, average waiting time go down substantially, right? Because P2 need to wait 0 for that. P3 would need to wait only for 3 milliseconds, 3 milliseconds for that, and then P1 would only need to wait for 6 milliseconds. So the average 0, 3, and 6 is going to be what? 3 milliseconds. So we go down milliseconds down to 3 milliseconds just by shuffling, which means that there's a very big variation in our metric of average waiting time, and that totally depends on the order in which we are executing the processes, which is a very big problem because now we are subject to this user-defined processes that are coming in. Obviously, they're random. The operating system doesn't have control over that. So, as I said, there are mainly two problems here. One is not good for time sharing because one process could simply hog up all the resources. The other problem is that there's a big variation in average waiting time. Questions so far? Okay. Next, we will take a look at shortest job first scheduling. Obviously, we are trying to improve the first come first serve scheduling. We will be able to do better if long each burst will be of time. Hence, this is a theoretical scheduling algorithm. We may be able to predict it, sort of approximate it, and we'll talk about that. But right now, it is a completely theoretical concept. So we would need to know how long each burst is going to be ahead of time. But suppose we did, hypothetical situation, we knew how long each was going to be. So we know that P2 is 3 milliseconds, P3 is 3 milliseconds, P4 is 24 milliseconds. If we know that, then we are going to work on that. So here we have to pick between P2 and P3. Suppose we picked P2. Maybe because P2's arrival time was sooner than P3. So because it was sooner than P3, it got it first. So we got P2 first, then P3, then P1. So this is sort of the same numbers here. And if we do this, what is the waiting time going to be? Well, it is the same example that we talked about earlier, right? 0, the waiting time for P2 is going to be 0, gets it right away. P3 has to wait for 3 milliseconds. P1 has to wait for 6 milliseconds. So if you calculate the average waiting time, this goes down to 3 seconds. So if we followed this shortest job first algorithm, right, you see, we are executing 3 seconds first. If we do that, then get a really good average waiting time, a very small number in comparison to the first come first serve. But the problem with this approach is that we do not know what each burst is going to be ahead of time. We can maybe do some prediction based on some history of each process, but I hope you see that right now it is sort of a theoretical approach, right? Because earlier, the difference between this and first come first serve is we were assigning, in the case of first come first serve, we were assigning a processor to a process as soon as it comes into the queue, as soon as it goes to the head of the queue, right? So it didn't have anything to do with its burst time. The only thing that mattered was its arrival time. Now, shortest job first scheduling is also non-preemptive. For example, we are not kicking any process out, right? So for example, if P2 came first and then suppose P3 comes in second, and if it is, higher priority, maybe we are not kicking you out, right? So once a process is executing that process until it gets completed, it takes the processor, which may not be fair to other processes. If higher priority process comes in, we may want to adjust our scheduling algorithm to accommodate those. So how do you predict burst times? We needed to know the burst times ahead of time for shortest job first. So how do you predict it? So maybe we can do some approximation. So short job is impossible to do it exactly because it's purely theoretical. We've talked about that. But an idea to approximate is to look at the set of burst times for each process. So if a particular process is taking maybe like 20 milliseconds and 24 milliseconds and 22 milliseconds, if these are usually the burst times for a particular process, maybe by looking at the recent history, we may be able to predict that, okay, maybe it'll take 23 milliseconds next, right? But we are definitely not going to predict that it's going to take 5 milliseconds next. So based on some recent history, we can do this prediction, and we can use that prediction as our number in the shortest job first criteria. It will work really well if the trend will continue. If the trend changes, then we'll have to adapt our predicted value, right? So over the course of time, we'll have to keep adjusting it. So what is the predicted value of burst time going to be? Well, some of it on previously measured burst time value, and some of it is not predicted burst time value. So we are using alpha as a parameter over here, which is a fixed constant. Alpha is essentially increasing or decreasing. It's a value between 0 and 1. And if it is 1, then the total expected value is totally not be measurable. Hard data, like no history, no prediction, hard data. But if alpha is 0, then so no real data, just predictions, right? So on both ends we will have some problems. So somewhere in the middle is going to be suitable, but again you can adjust it depending on the statistics for that particular process. Initial value of the prediction will start with some initial value for the previous, and that is a default constant. We are denoting the previously measured value for the first time, burst time for a process as t, and the subscript is n minus 1. N minus 1. So you're talking about the nth time. This is corresponding to n minus 1, the previously measured value. And for the prediction, we are using the Greek letter tau. So for the measured, t, for the prediction, tau. And both the previous measured value and the previous prediction, they are both corresponding to the same n minus 1 time step. What was it before? And then for the next time, right? This is previous. What are we doing for the nth time? For prediction for the next step. We are using sub n to the predicted value. So these are all predictions for burst times for a process. Questions about this slide? How we are going to be doing this? At least the parameters that are involved: previous predicted value, previously measured value, and the predicted value. All of this is to come up with what type of shortest, like when I say shortest job first, I'm talking about shortest burst time first. I cannot use that algorithm if I did not have any hard data. So instead of using hard data, which is going to be impossible, I'm using some predicted data. And that predicted data is based some on prediction, some on calculation, and some on real data, really measured values. Okay. Let's continue with this. This is as exponential averaging, or you're essentially doing a moving average for obtaining this predicted value. So sub n be actual length nth CPU burst. Now switching gears here. Now instead of talking about n minus 1 and n, you can also talk about n and n plus 1. So think of n as nth CPU burst is being used for actual data, actual length, not a predicted length. And we are defining now tau sub n plus 1 as the value for the next CPU burst. So how can I predict the CPU burst for the next time? N1? Well, tau n plus 1 is equal to the previous plus 1 previous, right? So tau is for actual length of the burst times. N is for nth time, n plus is for the predicted time, one time step ahead. Alpha is 0 and 1. So we have this is like I pointed earlier, alpha 0, alpha 1. If alpha becomes 0, this term goes out. And if it goes out, then we are essentially saying that we will predict based on the previously predicted value. The predictions are based on predictions in that case. Alpha 1, then we are the prediction is based solely on the measured data, actual data. So tau n plus 1 will equal tau n. If alpha is 0, that means that only the recent history doesn't count in that case. And if alpha equals 1, then our predicted value tau n plus 1 will be it solely based on what was it in the last step. Only the last thing counts in that case. No prediction. So now let's try to see what happens if we consider as half. So we are basing half of it on actual data and half of it on the predicted data. So our scaling is half. And tau sub 0, this is essentially our initial predicted value for the burst time, is 10, right? So we are using 10 time units as the initial value for the predicted burst time. Where we start, right? Tau is the time of the CPU burst time. In the black, so the black line is equal to the prediction. So our prediction is like a guess. But in the first time units, so the burst size for this particular process for the first time slot for the first time first time unit was just 6 time units. We predict 10. So what are we going to do? Well, we are going to have a value such that half of it depends on before and half depends on previously predicted value 10. So half of 10, 5, half of 6, 3. Add those two up. And we do that for every time we add blue line. So what does this show us? Well, the first thing I notice is that the blue line is tracking the black line, right? Which essentially means that my predictions are sort of closely related to the actual data. So this works, right? That's the first. This works is first conclusion, and it mainly works because I am trying to use some actual data in my prediction. That's why it works. But I also see that if there is a very change in the actual data, then it takes time for the predictor to catch up, right? So for example, a sudden jump from 4 time units on actual data to say 13 time units. When there's like that, because doing this half based on previous, half based on predicted, we can reach way to 13, even though we are not changing that 13, because we are relying on two aspects, real data as well as predicted data. So let me ask you this. If you wanted to reach 13 quickly, what would you increase weightage of? Would you increase the weight of actual data, or would you increase the weight of the predicted data, earlier predicted data? Actual data, that's right. So if you changed alpha in a way that the weight of actual data is increased and quickly snap to the black, right? But if you do that, what you are giving up is the advantage of predicting. So can play with that alpha process to to come up with an optimum alpha value and go from there. But this is one approach you can take to predict the burst time and then use that into your shortest job first scheduling. The next thing we'll talk about is the differentiation between preemptive and non-preemptive scheduling. So this is sort of a characteristic of a scheduling algorithm. Algorithms could be preemptive, and there are certainly some advantages there, and they could be non-preemptive. There are usually not many advantages with non-preemptive scheduling algorithms. Non-preemptive essentially means I'm not going to disturb a process. If a process is running, I'm going to let it complete. A new process can be dispatched only when a process terminates or switches to the waiting state. So if a process completes, then it is removed, it is moved away from, if the CPU resource is taken away from it, or if that particular process has a switch to the waiting state, which means it is doing some IO activity which is slow, or it is waiting for a certain event to occur, only then it moves away from the running state into the waiting state. So only if it moves away from the running state, I'm going to take it out. Otherwise, if a process is running, it is going to be running until it finishes it, until it terminates. A big problem of non-preemptive scheduling, such as the first come first serve scheduling algorithm, is that a process could come in, it is a very, very long process, and it doesn't allow any high priority or important jobs to go ahead. It is just it's a big sized process, and it is hogging up the CPU resource. Obviously, in that case, a preemptive approach is much better. And preemptive approach is what is real. In operating systems, you have preemptive scheduling because it brings about some fairness as far as many processes are concerned. So a preemptive scheduling is in which a running process may be preempted by another process based on some criteria. And that criteria could be priority, which generally is based on priority. A lower priority process can be preempted by a higher priority process. But that criteria could also be something else, maybe shortest job first, right? So for example, if you have only a small amount of time left for you to complete, you may preempt a process that has a longer time remaining to finish. So that can, the criteria for preemption may change, which sort of makes the preemptive algorithms to be more complex. But they are certainly useful and bring about fairness as far as the processes are concerned. Now let's talk about the shortest remaining time first. Whoever has the shortest remaining time, they get to go first. Shortest remaining time first is a practical approach to shortest job first, which was a purely theoretical approach with some prediction involved. We could approximate it, but SRTF does a much better job in doing a practical approximation. So what we do here is, when a new process arrives or a CPU burst is complete, we look at the remaining time estimates, and we are using TR to talk about the time remaining for each process. And we are going to schedule the one with the smallest time remaining to go use the CPU resource. Right? So this happens only when the process arrives or a burst is complete. Again, we'll take a look at some example to get a better idea about how this shortest remaining time first algorithm works. So in this table here, we have 4 processes, P1, P2, P3, P4. Their time of arrival the time at which they enter the ready queue are given to us. 0, 1, 2, 3 milliseconds respectively for P1, P2, P3, P4. And we also have some data about the estimated burst times. And this could be a station that we talked about, the moving average based on like half of the predicted value, half of real data. Whatever some estimates about their burst times. 8 milliseconds for P1, 4 for P2, 9 for P3, and 5 for P4. So who comes first? P1 comes first, right? So who will use the processor for the first 1 milliseconds? Who do you think gets to use the CPU resource for the first 1 millisecond? What do you guys think? P1, right? Obviously, P1. Nobody else is come here yet, right? The time of arrival is for P2 is 1 millisecond. Until 1 millisecond, there's only one process available. So during the first 1 millisecond, P1 will arrive and it will start its execution, right? But only for the first 1 millisecond. Because what happens at 1 millisecond? P2 comes in. When P2 comes in, it is going to have and P1 got 1 millisecond, so it has milliseconds remaining. So if you look at P1 and P2, because these are the only two processes that are in the initial 2 milliseconds, those are the only two. If you look at P2, the time for P1 is 7 milliseconds, for P2 is 4 milliseconds. So that will cause a preemption. P1 is being preempted by P2, and the criteria is the shortest time remaining. Not priority in this case, it is the shortest time remaining. So P1 is going to preempt P2, by P2, right? So P2 will use the CPU resource now, and will use the resource for 40 seconds. Why is that? And P3 came in comparison to P2. P4 came in seconds, but had 20 seconds as its burst time, still longer than P2's remaining, right? So P2 was the shortest remaining time, which essentially means that whenever P4 came in, it was still the process with the least time remaining. So it got to use the CPU from 1 millisecond to 5 milliseconds, at which time it is going to be able to complete. So I'm just talking about what happens at 3 milliseconds here. At 2 milliseconds, P3 will arrive with a remaining time of 9 milliseconds. P2's remaining time at that 2 millisecond mark is 3 milliseconds now. So P3 will have to wait. Similarly, P4 will have to wait at the 3 millisecond mark because P4 has a time remaining of 5 milliseconds. P2's time remaining at that time is 2 milliseconds. Still, P2 wins, so P4 has to wait. So at 5 milliseconds, P2 was able to finish, and I'm indicating that the process is yellow down arrow. That's how I'm indicating that it finishes there. Now what is going to happen at 5? This is, we talked about two things. It can be preempted at 2 times. 1, a new process comes in. 2, a burst completes, right? So the burst has completed. P2 has finished. Its burst is complete. So at 5 milliseconds, we re-evaluate the shortest remaining time process. Finishes, we have P1 time remaining 7. We have 1 second at the beginning, so we have 7 there. 9 milliseconds for P3, 5 milliseconds for P4. Shortest time, remaining time, P4. So P4 is going to start there. And it is going to use up all its 5 milliseconds. Why? Because it will time remaining and no other processes are coming in. So it will get to finish its burst. So from 5 milliseconds to 10 milliseconds, 5 milliseconds is going to use the CPU resource and it will get to finish. What is going to happen next? Which process will get the CPU resource next? There are only two options. P2 and P4 have finished. So there's a choice between P1 and P3. So who gets to go next? Alright, so P1 will get to go next because it has 7 milliseconds remaining. P3 has 9. So the shortest is P1. So P4, that's when we can preempt it. Then P1 resumes because it needs 7 milliseconds. With all 7 milliseconds, P1 will get to finish. After that, P3, the only process remaining, will start and use up all the 9 milliseconds after that, and it will be able to finish at the 26 millisecond mark. Now, notice here, the processes finished in the same order as their shortest remaining time. You see, P2, P4, P1, P3, right? 2, 4, 1, 3. It's the same order as 1, 4, 5, 9. But that is not a guarantee, right? So that is here. Are sort of very, very close to each other. That's how the numbers are sort of working out. So now let's take this and do some calculations. So we have the estimated burst times. And we are drawing versions of Gantt charts here for the processes. They are equally valid. Similar to the one that we drew earlier, where we have working for the first 1 millisecond, 0 to 1. P2 uses it for next 4 milliseconds, from 1 to 5 milliseconds. P4 uses it up to 10. Uses it for 10 to 26. You can also time column, time row, as row. Time unit P1 goes from P2, P4 from 10 to 71, 26, P3. So two versions of Gantt charts. Now using this, we can do, average waiting time and all those calculations. The next thing that we'll look at is priority scheduling. So how can we do this preemption based on priority? So we are considering the same set of processes before. 2, 3 milliseconds each, respectively. It's the same, but we are trying to indicate the priority of each of these 4 processes. Notice over here, the highest priority process is P3 because it has the lowest priority number, right? So a lower priority number indicates higher priority process. So let's take a look at how does preemption work in terms of a priority scheduling algorithm. We are going to start with P1 again because it's it is the one that arrives first. So P1 arrives and starts. Until the first 1 millisecond, I don't need to worry about what happens. At 1 millisecond, P2 is going to come in. And when P2 comes in, you can see that the priority of P2 is higher than P1, right? Because it has a lower priority number. So P2 is going to preempt P1. P2 arrives, has higher priority than P1, in that case. Now the preemption, the criteria for preemption now is priority. At 2 milliseconds, P3 is going to arrive. It actually has the highest priority, which means that it is going to preempt P2. At 3 milliseconds, P4 comes in, but it has the lowest priority, so it'll have to wait. P4 doesn't do anything. P4 is going to have to wait. But P3, because it has the highest priority, it is going to get the CPU resource for 9 milliseconds, and it will be able to finish at the 11 milliseconds mark. After which, we look for the next highest priority process, which is P2. We had already worked for 1 millisecond. We were left with only 3 milliseconds. Over here, 11. At 14 milliseconds mark, P2 was able to finish. And then we went looking for the highest priority next. P1 average 1 millisecond there. It has remaining. So 14 to 21 seconds to run on the CPU, and it will get to finish. And whatever remains on priority, we didn't need to work on P4 there, right? So from 21 milliseconds to 26 milliseconds, P4 is going to use the resource and finish at 26 milliseconds. So the order in which we have sort of executed these processes has changed, because now we are not looking at the shortest remaining time as our criteria for preemption, but we are looking at priority as the criteria for preemption. Now we can again draw a Gantt chart for this. Process, time of arrival, burst time, and priority included. This arrived on the previous slide. And this is the second version of the time. The way you read it is, for example, right? So P2 is on the processor for 17 seconds. Again, you can use this data to find out the average waiting time and all of those things. P3 finished first, P2 finished next, P1 finished next, P4 finished next, right? Again, it so happens that the order in which our processes have completed is the exact order in which their priorities were listed, right? So P3 got finished first, and P is the highest priority process. So process finished in order of the priority. Is this going to be always true? For a priority scheduling algorithm, is that going to be always true, that higher priority process will always finish first? No, that's right. It's not guaranteed, because given at the first 1 millisecond, it will finish, right? So even if it's completed first. So it also depends on the burst times and their times of arrival. So this is just the way the numbers have worked out in this example. All right, questions so far? Things are going pretty smoothly. So these this lecture is not really like it's very intuitive, this content. But if there are questions, please let me know. I guess the only real confusion can be, is it preemptive or non-preemptive? And if it is preemptive, then oh, here is an interesting question. If it is preemptive, then you ask, what is the criteria, right? Is it priority or is it shortest remaining time first? If I say priority, okay, fine. There are different numbers for the priority. But if I say shortest job first, shortest remaining time first, what if among the remaining processes they are multiple with the same time remaining? What happens then? You guys see what I'm saying? So suppose we are using like a preemption, like a remaining time first algorithm, and we are doing this preemption based on time remaining. What if it is the same number, same time remaining for more than one process? Just pick the one with the earlier time of arrival. That's absolutely right. So you pick the one that got the CPU's attention long time ago, right? So if there was a process, so something like a circular queue, right? So if you if you worked on P2, then you worked on P3, then you are, you know, going to, you don't want to go back to P2 because P2 already got that attention, right? So that would again be based on either the time of arrival, but if that data is not available, you base it on whoever got to go a long time ago, right? Next, all right. What are some hidden dangers? If you are doing priority scheduling, a preemptive priority scheduling, there is a problem with this. Even though it might not be very obvious, there is a problem, a hidden danger with priority scheduling. And it is indefinite postponement. Think about a scenario in which the operating system is continuously having to work on higher priority processes. And if that is the case, a lower priority task may get postponed indefinitely because there is always going to be a process and they are supposed to keep coming in, right? And if a higher priority processes keep coming in, there will be no progress on a low priority task. That's a problem. And the solution to this can be aging. Aging is essentially adjusting the priorities of a process based on how much they have waited. So, you know, if a process is waiting for a long time to get the CPU's attention, increase its priority. In other words, lower its priority number so that they eventually become important enough or become higher priority enough so that they can get the CPU resource. Now let's talk about round robin scheduling. So this is a more fair way of scheduling CPU, doing a CPU scheduling. This is specifically designed for time sharing systems, such as what they happen in a Unix operating system. So time sharing is what? Multiple processes using one CPU resource, but they're trying to use it based on a timeshare basis. What we are going to do is we are going to define a fixed time slice, also called as the time quantum. This would be the time slice or a chunk of time for which a process can get the CPU resource. But after your time slice expires, you get kicked out, right? So you will get preempted after your time slice expires. And if this time slice is a constant number for all the processes, that can help with bringing about some fairness in how the processes get executed. Sort of a nobody gets left behind approach. Now, the ready queue is going to be circular in this case. So whoever gets preempted will go back to the end of the queue, right? So it's a circular queue in this case. A process is preempted if it is still running at the end of the time slice. So if your time slice is or time quantum has expired, you will be preempted. Bounded wait, which essentially means that what is the highest amount of time, longest amount of time a process will need to wait. Well, the longest, so suppose there are n processes, right? If there are n processes, then suppose there are 5 processes, right? If there are 5 processes, then they are essentially getting 1/5 of the CPU time, right? So they are getting 1/5 of the CPU resource because they are doing this as a time share basis. But how long at the maximum will they need to wait before they get the CPU's attention? Well, if there are n processes, then they will need to wait for the next time they could get the CPU resource would be the maximum. This is the bounded wait, is n-1 times the time slice. So whatever the time slice is, time quantum is, you multiply that by n-1. In our example, we said 5 processes. So you would multiply that by 4 in that case, and that would be the maximum time for which a process will need to wait before it can get the CPU resource the second time, the next time. So it has a bounded wait. So that's helpful. It's never a indefinite postponement. Now let's work through a round robin scheduling algorithm. Here we are using the time quantum of 20, which is 20 time units. So time slice or time quantum as 20 time units. We have 4 processes, P1, P2, P3, P4, and their burst times are 53 time units, 17 time units, 68 time units, and 24 time units. So how are we going to do this? Suppose they are all coming in to the ready queue at the same time. Maybe P1, P2, P3, P4 in that order, right? So suppose P1 is coming first, P2 next, P3 next, P4 next. But their arrival times are not necessarily important. What is important is how they go about splitting up this CPU resource. So for the first 20 time units, because that's the time quantum, P1 will get to use the CPU resource. After that, P2 is going to be next. It's a circular queue, by the way. So P1, after it gets preempted, it has gone back into the very end of the queue. So P2 will get to go next between 20 time units and 37 time units. It doesn't even need the total time slice. It only needs 17 as its burst time. So P2 actually will get to finish at 37 time units. It's done. After that, we are going to need 20 the time slice of 20 time units for P3. So 37, that takes us from 37 to 57. 20 more for P4. So at this point, let us try to look at how much is left. So P4, we have 33 left. P2 is done. P3, we are left with 48 time units. And P4, we are left with 4 time units. As I said, it's circular queue. So P1 got preempted first. That's what will come in to the running state now. P1 needed 33. Out of that, we are going to give it 20 right now. 77 to 97. P will get to go next. We are down from 48 left to 28 left. P4 just needed 4 more. So that takes us from 117 to 121. P4 will get to finish at this point. We are going back to P1 now. And P1 just had maybe 13 left. Right, 13 left. So that takes us from 121 to 134. P1 will get to finish. And P3 had some remaining. I think P3 went two times, so that was 40. It has 28 left. Because it is the only process remaining, it can go twice and be able to finish at 162 time unit mark. So all the processes are getting sort of an equal share, and they are getting preempted by a process that was waiting the longest for a processor in a circular queue manner. So that is an example of round robin scheduling. No priority here, but we are using a time quantum of 20. Questions about this example? Let us also note the order in which the processes have completed. It looks like we went 2, 4, 1, 3, right? So if you look at 2, 4, 1, 3, it looks like they are in the same order as the burst times, right? So, but I did not get why this is advantageous. We are giving a limited amount of time, but for each process to work on, right? So this is, so you see this, no matter how many years it got done, right? Everybody is sort of making progress simultaneously in this case. You see that? I thought finishing P1 at 117 would finish P1 first. I thought finishing P1 at 117 would finish P1 first. No, P1 is finishing 4. So P1 is 2 minutes. We work 20 here, 20 here, and that's when it finished. So, is the order of the queue always the same order of the time of arrival? Is the order of the queue the same? Yes, that's right. And it is circular. So whoever gets kicked out goes to the back of the queue. So they will get it next, the CPU next, at the very end of the remaining processes. Even if something arrives while it is processing something in the middle of the queue. Even if something arrives while it is processing something. So each time quantum is 20, right? So nothing can be preempted before 20 time units unless the burst is complete. So you look at the next process to work on only after a completion of the time quantum or completion of a burst. And at that time, you are essentially going to be looking at what is the head of the queue. And it's a circular queue, right? And when you look at the head of the queue, you will look at the process that got the CPU resource the farthest out in time, right? So if we have not worked on a particular process in a very long time, they are going to get priority. So if a new process comes in, they go to the back of the queue, right? So we are trying to sort of focus mainly on the fairness of the processing. All right, let's move on to impact of the time slice. because I've used a time slice of 20 time units. What if I made it too small? Or what if I made it too big? Well, if I made it too small, what would happen? If instead of making it 20 time units, what if the slice or time quantum was chosen to be 5 time units? You see, if you did it as 5 time units, what does the Gantt chart look like? Well, you do 5 times after 5 time units, you would do P2, after P3, and P4. In a matter of 20 time units, you would have switched or done a context switch from P1 to P2 to P3 times, right? So if you choose a very small time slice, then you will have e-processing. However, the way sharing, however, your computer system is going to become very slow because you now have the overhead of doing context switching, which essentially means the processor is spending time moving from one process to the other, as opposed to making progress on a process. It is spending time doing switching from one process to the other. That happens is too small. So you're going to need to adjust your time slice such that it is small enough for this processor sharing, time sharing to happen, but it is also not larger than the context switch time, right? So you want that time size to be much larger than the context switch time. Context switch time essentially means how much time does it take for a new process to use the CPU resource after the old process has left that CPU resource, right? That's the switch, context switch from one to the other. So you would want time slice to be small, however, it needs to be larger than the context switch time. But if it's too large, then it almost becomes as bad as the first come first serve scheduling algorithm, because then there's no real fairness. If it becomes too big, then you're allowing each process that came in first to end first, and it is going to tend towards a first come first serve scheduling algorithm, which has its own problems. A process can just hog up the CPU resource forever. Right? So then we are not really having any kind of fairness in terms of scheduling processes. So you would want your time slice chosen in such a way that it is not too small nor too big. You would want it to be larger than the context switch time. So this data actually can help us figure out what is the best time slice. This is the same plot as before. We are looking at the noise on the y-axis, in milliseconds on the x-axis, and so the peak is around the 3 millisecond mark. The area of the triangle is greater than 80% of the rest of the area, which essentially means almost 80% of the activity that's going on has been pretty small. The rest 20% are in the higher range. So make 80% of the CPU burst shorter than the time slice. That's what is your goal going to be, to pick the balance between the too small time slice and the too large time slice. You want to ensure that your time slice is much greater than the context switch time, and you're choosing a value such that 80% of your CPU bus, right, the area of this part is 80% than the total area. And if that and it's going to be a particular time slice value that is going to allow that to happen. That's how you're calculating your suitable time slice value. Okay, that will do it for this lecture. I think you guys can go ahead with the activity now. I'll stop recording here.